Hello, Bobcats. In this video, we're going to take a look at how to write a balanced reaction for the formation of a substance from its elements, and then where to go to look up a numerical value for the enthalpy change for this reaction. If you haven't already been using your textbook, I also wanted to take just a moment to point out that if you go to your Sapling Learning account, over here on the right I'm showing a snip from mine, and over in the upper right hand corner you'll see your name, and then on that right hand bar, if you scroll down a little bit, you'll see the link to our textbook. Just wanted to make sure everybody knew how to access our textbook. Formation reactions are a special type of reaction that are defined to form 1 mole of a product from the elements in their standard states. So as an example of a formation reaction, we have this one for the formation of barium chloride. Notice that there's a coefficient of 1 on the product, barium chloride. We don't write the ones usually. And on the left-hand side, the reactant side, we're showing the elements in their standard states. So we're showing barium, since we need 1 barium, and then Cl2, because we need 2 chlorines in this product. So each one of these has a coefficient of 1 associated with it. They don't always have 1s, and sometimes they have some pretty strange coefficients. For instance, if we're going to make aluminum chloride and have a coefficient of 1 on aluminum chloride, we're going to need 1 aluminum atom, which aluminum provides quite nicely here, and then 3 chlorines. Well, that gets tricky because chlorine is a Brinkelhoff, and the Brinkelhoffs occur as diatomic molecules, so they'll have a subscript of 2. So in order to get 3 atoms of chlorine, we have to use a coefficient of 3/2, because 3/2 times 2 gives us the 3 chlorines that we need. So often these formation reactions will have very strange coefficients on the reactant side because the product must have a coefficient of 1. When we write formation reactions, the elements are expected to be in their standard states, and standard state means the state of matter, solid, liquid, or gas, that the substance has at a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. So this is slightly warmer than typical room temperature, and 1 atmosphere is normal atmospheric pressure. So as an example, if we're talking about iron, we would write iron with the phase of solid because iron is normally a solid at room temperature and normal pressure. If we're talking water, its standard state would be a liquid, and if we're talking about oxygen, its standard state would be a gas. The enthalpy changes associated with formation reactions are typically tabulated in a general chemistry textbook. You'll find them in our textbook in Appendix A2 in the very first column of data in that appendix. If you look at the table of contents in your textbook and you scroll down to the very bottom where there's a heading called back matter, the appendices are listed in that section. Something I'd like to note about notation here. Standard conditions are implied by this degree sign. So when we write delta H sub F with the degree sign means that we're working at 25 degrees C in 1 atmosphere. And the F subscript down here means that this is for a formation reaction. These next 2 columns that you will see in the appendix are for Gibbs free energy and entropy, which are topics that will be covered in Chem 1342, the continuation of this course. Now, let's see exactly what this number here for the heat of formation or enthalpy of formation of silver oxide refers to. All right, so we're going to pull that number. The heat of formation is negative 31.1. That's just reading this number out of the table. This is the change in enthalpy for the formation reaction for Ag2O. So we know that on the product side, there must be 1 mole of silver oxide. And on the reactant side, we need to have the elements in their standard states. Well, to make silver oxide, we need 2 atoms of silver, and silver is normally written just Ag, that's its standard state, Ag solid, and we have to put a coefficient of 2 in front of it to get these 2 atoms of silver. And then oxygen is going to be a little trickier because the standard state for oxygen is O2 gas, but we only need 1 oxygen, not 2, so we'll have to put a coefficient of 1/2. There we go. This is our formation reaction. So this number that you're pulling out of the table, the negative 31.1, is the enthalpy for the reaction. 2 silver solids plus 1/2 oxygen gas yields Ag2O solid. A special case occurs when we consider the enthalpies of formation for elements. If we're to write the formation reaction for the element chlorine, that reaction would look like this. Cl2 gas yields Cl2 gas. Since the products and the reactants are exactly the same, the change in enthalpy for this reaction is 0. That's simply due to the definition of formation reactions. And this will be true for all elements. So the delta H of formation data for elements in their standard states are usually not shown in tables or even given to you in a problem because they are all 0. So you need to recognize if you have an element in its standard state, its delta H of formation is 0. Let's write the reaction for the formation of ethanol in its liquid form and then look up its delta H of formation in our textbook. So to be a formation reaction, we're going to make exactly 1 mole of product. So the product side will show 1 mole of C2H5OH in its liquid state. On the reactant side, we're going to have the elements that come together to make this. And there are 3 of them. There's carbon, hydrogen, and oxygen. Carbon in its normal standard state is a solid. And so we would write carbon as C, solid. And we need to put a coefficient of 2 out in front of it to match the 2 that we have on the product side. For hydrogen, hydrogen's normal state is a gas. And so we'll write H2 gas. This is also one of the Brinkelhoffs, so we have to write a subscript of 2 on it when it's in the elemental form. Over on the product side, we have a grand total of 6. There are 5 of them written as the H5, and then 1 more written out there with the OH. So that's a total of 6. So we need to put a coefficient of 3 out in front of the H2. And then the last element we need is oxygen. So I will try to squeeze in O2 gas here. And for oxygen, we only need 1 of them. So the coefficient that we'll write out in front on oxygen is 1/2, because 1/2 times 2 will give us 1. To find its enthalpy of formation, we'll go and take a look at the table in Appendix 2 of our textbook. And notice that ethanol appears twice. It is listed both as a liquid and as a gas. So the value that we want to pull is the one in its liquid state. And so the delta H for this reaction represents the delta H of formation at standard conditions, which is going to be a negative 277.6 in units of kilojoules per mole. Our objectives for this video were to write a formation reaction and to find the heat of formation from the table in our textbook, and I think we've accomplished that. Eat 'em up, cats.